So the second speaker this morning is Eric Samperton from UC Davis, and he's going to tell us about computational complexity and three-manifolds and zombies.
Cool, thanks for having me. So I'm going to do the opposite of Arnaud. I'm going to mostly be on the slides, and occasionally I will defer to the chalkboard. So don't worry about these things at the moment. I'm just using them because opposite to him, I'm better at drawing on the chalkboard than I am up here. So what I'm going to talk about is the computational complexity result for a certain family of invariants, of three manifolds. They're very classical invariants. And yeah, so maybe I'll define those first. So, our reduction, so fortunately Arnaud gave us kind of quick introduction to complexity. So our reduction, when later on, will be from circuit satisfiability over here. So I'll discuss that in more detail as we go. And the hard part is going to be introducing different circuit models, because this circuit model, CSAT, isn't quite the right thing. So we're going to have a series of different circuit models, a series of improvements that kind of works us closer to the invariant we're actually after. So we kind of saw in our notes talk that and we're going to do the same thing, that we're going to kind of work towards the middle. We know something is hard, and we know what we'd like to show is hard, and we just have to kind of whittle away from both sides until we show the two things are sufficiently the same. And that's what these circuit designs are about. And the kind of critical thing is getting the right notion of alphabet, and that's where all of the topology comes in. Then there's some group theory, some more topology, showing that that alphabet is a good alphabet to use, and the main theorem will follow. So what's the invariant we're after? We're going to fix a finite group. And you should think of this as fixed once and for all. It is not part of the input. In our main theorem, it's going to be a nonabelian symbol group. So you should think A5, the smallest one. So, and our input, our computational input, is some kind of space, some nice description of a space. So for us, our spaces are going to be three manifolds. They'll actually even be homology spheres, I can guarantee that. Or they can be non-diagrams. Although what I discuss in detail, I'm just going to stick to the three manifolds. So the invariant we're after comes from counting homomorphisms. So if you have a space X and you have a group G, what's something you can do? Well, you can count maps from pi1 of X to G. So what we want to know is what is the complexity of this problem as a function of X, although the answer to this question depends on G. So in order to understand this invariant, we have to introduce another one, which is a little bit contrived, but it is definitely important. So instead of counting maps, we could count kernels. So here, gamma is a normal subgroup of pi1 of our space, and we want that the quotient by that normal subgroup is isomorphic to G. And this is important because of the following formula, that the number of homomorphisms from X to G is some weighted sum of the number of kernels whose quotients give you a subgroup of G. So this comes from the fact that J, so if you have any map from pi1 of X to G, it has an image J. And well, it has a kernel as well. And for a given image in a given kernel, there are this many maps to G with that image of kernel, all J. It's just the first isomorphism. So in order to understand the complexity of H, we have to take into account that it's always of this form. And that's going to make the results look a little technical. But if you understand this, you should hopefully see why we care about it. So for knots, we can do a little bit more. There's another invariant we can look at. It's a little more refined. So now we can fix an element of the group, C. And now we will count maps, not just arbitrary maps from pi1 of K to G, but maps that send some fixed chosen meridian to C. So you're fixed, you can think of this as you have an arc on the diagram and you're fixing a color of that arc. And there's a similar invariant where you can count normal subgroups, similar to Q state. So now our isomorphism from pi1 of quotient can't just be isomorphic to G. We want the isomorphism to take this chosen meridian to C. So the meridian is totally arbitrary and just kind of an artifact of the fact that there will be more symmetries in the case of knots. just like we had symmetries that's on J multiplicities, there'd be more here if we didn't break one of those by picking a color for a meridian. So is everyone okay with the invariant we're studying? Okay. So what's the theorem? So now we're going to take G, it's a nonabelian simple group, and we more or less showed that this invariant is as hard to compute as you could expect it to be, given that it's always of the form on the previous slide. It's this weighted sum of automorphisms, of representatives of automorphisms. So, and it's hard even if the input is a homology three-sphere. So you give me a triangulated three-manifold, you can even promise to me that it's a three-sphere, that it's a homology sphere. And what we show is that counting this Q invariant is sharp P complete by a parsimonious reduction. So, so what is sharp P complete? I mean, this is a kind of counting analog of NP complete. So our node showed us what it meant to be NP hard, and there's a similar notion of sharp P hard. And roughly, we'll see as we go, but roughly we're going to take one of these things, one of these circuits, these in CSAT, and we're going to cook up an integer homology three-sphere M, so that this number, the number of inputs to the circuit that make the output 1, is exactly this Q invariant of the manifold. And we do a little bit more, because what we're really after is H. So to understand, this just says something about Q, to get some guarantee about what H looks like, we do more with our reduction. So our reduction guarantees that that the maps from pi 1 of M to G are either trivial or surjective. Right? So we rule out this QMJ being non-trivial for any proper subgroup J. So we have to do more work to guarantee that. We have to do more work with our M to guarantee that. So we have a similar theorem for knots. So this one is written up already. Yes, question.
So G is a fixed group.
G is fixed once and for all. Yeah.
But it's simple and nonabelian.
Yes.
Right?
Okay. A5.
Okay.
Does this say anything about the question of whether Q is non-zero or not?
I'll get to that in a moment.
Okay.
So, so we have a similar result for H. The answer is yes. So notice, and it's because of this guarantee that all of the homomorphisms are either trivial or surjective. Because in this case, the number of homomorphisms, well, there's one, because there's always a trivial homomorphism. And then every other one is surjective, and well, that means the number of homomorphisms looks like that. So what does that imply? That implies all of these decision problems are NP complete. So what are we doing here? In the first one, we're given a triangulated homology three-sphere. We want to know, does its pi 1 surject onto G? Well, that's going to be NP complete. You can also ask, well, does its pi 1 have any map whatsoever to G that isn't trivial? That will also be NP complete. And you can do the same problems for these not. Ask the same questions about these non-invariants. So there's a very succinct corollary that comes from all of this. In the special case, if you look at G as A5, then there's a corollary that deciding if a homology three-sphere has a 5-sheeted cover, that's connected, of course, is NP complete. And we can do a little bit more. We can actually promise that it has no covers of a smaller degree. And there's nothing special about 5 as long as you pick an n bigger than 5. So n could be a trillion, and it's NP complete to decide whether a homology three-sphere has a trillion-sheeted cover, even if you already know it doesn't have any covers of smaller degree. So does that answer your question? Okay. So some remarks about these theorems. So this reduction to H, so there are different types of reductions, right? So the strictest notion is what we give in the statement of the theorem, this notion of a parsimonious reduction. So that means if you give me one of these Z's, I cook up a manifold so that that Q invariant is exactly the number of solutions to this Z on the nodes. But you can ask for weaker types of reductions. So this reduction in H, though, because H is of the special form, can never be parsimonious. It can never be the strictest type of reduction possible. But our theorem says it's, well, we made it as strict as possible given that this H is this form where it's a sum of of these kernels with multiplicities. So in this case, we say our reduction to H is almost parsimonious. So the theorem for, well, a version of the second theorem for links was proved, a weaker version by Crovey and Russell. So they showed the problem was sharp p-complete, but the reduction, it's not even what's called a weakly parsimonious reduction. So they don't get to show, for instance, those corollaries I have. They don't know that the existence problems are NP. And so prior to the first theorem, there was nothing special about three manifolds. We could have asked about arbitrary simplicial complexes or even arbitrary finitely presented groups. You could ask, well, what's the complexity of counting homomorphisms from finitely presented groups to A5? And nothing was known about that. It was an open question, I guess, in kind of group theory complexity literature. We got all the way down to three manifold groups, which are very special, right? Because arbitrary finitely presented groups are a much bigger class of groups than three manifold groups. And the theorems, we can also, in principle, we can improve the statements to allow not just a single finite group. You could count maps to any list of finite simple groups, and these invariants will be hard to compute as well. And I didn't say much about it, but in this H invariant, in the case of knots, we have this choice of this fixed color, and you can ask, well, what's going on when you have different colors? And if the colors are, if there's some automorphism of G that takes C to C prime, then you know these invariants are the same. These numbers are the same. And what we expect is if there's not such an automorphism, then you can decouple the values of these invariants. You can construct three manifolds that take any arbitrary values of these two, for these two different choices of the color. Sorry, you can construct knots. So that's the theorem. How do we prove it? So it's a circuit reduction. We start with CSAT. So I have this on the board, this kind of schematic of this definition. So CSAT is a decision problem. You're given a Boolean circuit, and you want to know, is there some input that makes the output 1? Right? So is there some way to assign 0, 0, 1, 1, or something like that to this input so that the output up here is 1? And that's a decision problem. But this decision problem is in NP. It's actually NP complete. And there's a corresponding counting problem. Every problem in NP, once you've picked a notion of predicate, there's a corresponding counting analog. So you can think of this, if you have an NP Turing machine, then you're counting the branches that output with the yes. So the counting analog is just counting solutions. And the same theorem that shows that CSAT is NP complete, the same proof that shows that, actually shows that the counting analog of CSAT, number CSAT, is sharp p complete via parsimonious reduction, so in the strictest possible sense. So this tells us we can take number CSAT as our starting point. So what is the idea? So how do we go from this thing to a three-manifold? So I'm only going to discuss the three-manifold case in detail. So this slide is basically defining the notion of parsimonious reduction. So you're given Z, this circuit. We need to construct a triangulated homology 3-sphere, M sub Z, so that this invariant Q is exactly the same as the number of solutions to Z. And because of that second part of the theorem, we also want the second condition that, we want the second condition here, that there aren't any smaller quotients. So how do we do that? What's the intuition? So, well, if you've ever looked at topological quantum computing, we're basically doing that, except nothing is quantum. So we're going to study a combinatorial TQFT. So here's the setup. If you have a three-manifold, so we're going to think of our three-manifolds as coming from Hegar's modes. So I have a handle body down here, H0. So I've indicated the curves that bound this in red. And I have another one up here, H1. These curves bound the other side of this. So I'm going to glue them with some mapping lines. So don't worry about how I've drawn this surface in a funny way. We'll get back. And if I have a homomorphism from pi1 of this three-manifold, well, you can think of that as coming from a homomorphism of pi1 of this surface that satisfies conditions. So what are the conditions? Well, if I have a map here, and the pi1 of this surface, when we map it into pi1 of m, degenerates, because this is a Hegardt surface. So if this map from the surface gives you a map here, that means it factors through both handle bodies. So we have two sets of constraints. We're interested in maps from this surface to G that factor through this bottom handle body, these red curves, and so that, I have an error here, should be F. We want phi of F. So phi is our gluing map. So when we twist this surface up to get this other surface up here, we need it to factor through this top handle. So these are constraints. So here there aren't really constraints to talk about other than is there an output that's 1? But it's kind of a constraint satisfaction problem. And when I word it this way, the number of maps here is the number of maps from the surface that satisfy these constraints, then it's a constraint satisfaction problem. So are there any questions about that?
So you're going to tell us how to write the constraints.
Yeah. So an immediate issue when you're trying to compare these two things is that, well, a mapping class is acting on maps from the surface to G. So let's write that. So we have this big surface, sigma and G, and the mapping class group of that acts on the set of representations from pi1 of it to G. So this is a plane map. So I have to keep track of base points. That's another kind of annoying thing. But I'm not going to bother doing this. So if I have a mapping class acting on here, and then it's acting on the set, there's an induced action on the set, you think of that as kind of processing information. So an element of this set is a state of your system. And when you start twisting it up with mapping classes, you're doing a computation. So that's exactly what people do in topological quantum computing. Just nothing. Here in topological quantum computing, this would be a Hilbert space. You'd have some unitary action in the mapping class group. But we just have this finite set, and we have a permutation action. So now, something I've said here, so this doesn't look local, right? I could have some super complicated mapping class, and how does that look like a circuit? Because circuits are broken up into gates. Well, we're not just having arbitrary, we're not going to consider just arbitrary elements of this mapping class. We're going to have very controlled ones. So what we need are binary gates, right? So just like up here, the gates, you're only ever feeding 2 strands into a gate. We only want to feed 2 small subsurfaces into a gate. We want to keep track of those subsurfaces. So what we do is we clump them up. So you really want to think of, if you have a map from pi1 of this big surface to G, you want to think of it as a map from pi1 of these smaller surfaces to G, as a sequence of maps. So you have the value on the subsurface here, the value here, the value here. So these are the computational digits, the maps from pi1 of this surface to G.
Your picture of Z, everything was sort of tree-like, but if you recombine it, it goes down.
No. So yeah, I still haven't answered your question yet. So your first question. So I'll get to that in a moment. So the answer is on that other board. So first of all, we want binary gates, and the way we do that is to break up the surface like this. So what we really need to understand gadgets, if we want to replace an AND gate with some mapping class, we need to understand the mapping class group action of these smaller computational subsurfaces. So the binary gates are going to be elements of a smaller, so now I have a genus 2G surface. So G is the genus of these little plants lined up in a row. And we take 2 of them that are neighbors, we can start twisting them up and ask, well, what gates do we give? So what that means is we want to understand the image of this action inside the symmetric group on this set. So I'm going to call this set, I'm going to define it here. So the set is R hat of 2G. So this one is R hat, sorry, R hat of NG. So R for representation sets, the set of all representations from Pylon of this genus NG surface to G. And here we have just a genus 2G surface. So what we'd like to know is, well, what can we say about this action? So there are two issues, even all this. The first one is what Saul's getting at, which is that these mapping class groups, the action, well, it's a group that's acting. So all of the gates, if you just give me a Dane twist and say, well, how does the Dane twist affect this set? Well, it's a bijection, it's a permutation. Whereas up here, an AND gate, well, is definitely not bijective. So what we need to do is use reversible computing. So we need to study reversible circuits. So this is a Boolean circuit with ands and ors and nots, and we can study reversible Boolean circuits. So that's what this next board is about. So, and to be fair, this is a standard enough construction. We couldn't find a proof anywhere that this problem in the literature, but people have been studying reversible circuits since at least the 80s. And so if you look at kind of quantum computing papers, you see this construction that takes you from CSAT to this RSAT, as no one ever calls it that. So what is RSAT? So R for reversible circuit. So now you're given a circuit Z, and you don't have AND gates and OR gates and NOT gates. You have a different type of gate. The gate, so all of these black boxes, each one of them is some element of a symmetric group on pairs of values 0 and 1. So you have a symmetric group of 0, 1 squared. So you're feeding 1, 0, 1 on this side and 1 in from this side, and well, you have some permutation. And it outputs a 0 or 1 here and a 0 or 1 here. And this is a bijection. So this circuit, though, unlike over there, where we're just allowed to input anything we want into the bottom, we're asking what comes out the top. We're going to kind of specify that half of the input variables are preset. They're all 0. And same thing with the top. They're all 0. Let's imagine if we didn't do that. Right? So you have some output, and you say, well, what is there an input so that when you input it, you get that output? What's the answer?
Yes.
Yes, it's always yes, because this is a reversible circuit. This whole thing is a bijection. So you're feeding strings of 0s and 1s, and you're getting some other string, and it's a bijection. So you can't just fix a single thing at the top and say, can I find something so that the input gives you that? Unlike over there, right? With the non-reversible circuits, we're just fixing 1 at the top and saying, well, how do we get 1 by inputting things at the bottom? So we have to kind of spread out the constraints, both in the top and the bottom, because of the reversibility restriction. But this turns out to get us much closer. It seems like kind of bizarre. Why do I have to do that? Well, it turns out to get us much closer to what we're doing over there. So the fact that I have a fixed 0 here, if I'm looking at solutions, well, I should tell you what a solution is first. So I want an input. So I want an input here. I process it, and then I get an output. What I want is an output where this first strand, the value is 1. So that's what I have written here. So I have an input. So this x is of length n. And then you have these n ancilla. These are called ancilli. And you want to know, well, when you apply your circuit to this input, do you get an output strand where there's a 1 in the first position? And of course, you need 0s in the last n positions. So this problem is also Sharp-P complete by a parsimonious reduction. So there's a way to go from that to this. And what you do is more or less, anytime you have a non-reversible gate over there, say an AND gate, you introduce a new variable. So you put a new strand in, and you dilate the gate to make it a bijection. And that new strand is where these ancilla come on. So back to what I was saying, though. So these ancilla are actually very natural, considering what we're doing over there, because we have constraints coming from the Hayward surfaces. If I want to map from this surface to G that factors through and gives you a map from the three-manifold group to G. Well, if you pick any one of these red curves, then f, the value of f on that red curve, well, any base points, but the value of f on that red curve has to be trivial, because that curve bounds at this. And the fact that that's trivial is exactly like saying it's the value of the ancilla is 0. So I should have made that color red. So that's a top ancilla. So if I have a top ancilla up here, well, that's like the top Haggard curve over there, the value of f on that being 1.
So then what are the actual variables?
Just zeros and ones.
Yeah, but so it's like curves of Georgia outbound disks.
What are the actual variables? Over here?
Yeah.
Well, you can look at a generating set of the pi 1, just pick some system of curves. We don't actually need to think about it. We just, but you have some standard generating set of the pi 1, the surface, and you're just looking at the values of f on that. Not all of those give you homomorphisms, but that's okay.
I think so, maybe. He's not yet turned the two problems into one another.
Yeah, I have it.
Okay.
It's a long story. Yeah. Yeah. So
You just made progress.
yeah. So we're getting closer, right? This is reversible. That's reversible. We're getting closer. But there's another issue. The other issue. So these are arbitrary. These gates are arbitrary bijections on pairs of Boolean variables. But we don't get arbitrary bijections over there. So more or less what I'm saying is that when I look at how this mapping class group acts on this set here, you don't get the full symmetric group of this set. There are constraints because it's topology. So what are the constraints? Well, one constraint is that there's another action on this set. So the set of homomorphisms from the pi 1 to the surface, this representation set, has an action by the automorphism group of G. So aught G acts here. So these two actions commute. So that severely constrains what the image of this can be. So we have to introduce a third circuit model. Well, we don't have to, but it's convenient to. And it's going to require more. So here we had these Boolean variables, but now we're going to have to pick a bigger alphabet. And what we want is not just reversible circuits. We want reversible circuits over some alphabet that has a symmetry. And we want those circuits to be equivariant with respect to that symmetry. So that's what this Z set is. Z for zombie. So we have a finite group K. This will be the automorphism group of G later. We have a finite set, or a finite K set. And we're going to assume something about this K set. It's just kind of a technical assumption that is very useful. So there's going to be a single fixed point of the action of K on A. So we call it Z. So Z is in A. And this is the only fixed point. And moreover, the other orbits are free. So we'll get back to that, why that's perfect. And then we're going to pick two sub-alphabets, so A for alphabet. Up here it was a Boolean alphabet, but you should think of this as some big finite K set. You know, they have 100 things. And we're going to pick two subsets. We'll have I, which is the initialization constraints. And we'll have F, which are the finalization constraints. So again, working closer to where we want to be, A is going to be some subset of maps from pi 1 of the small surface to G. So that would be R hat. So RA is going to be some subset of R hat of G. Now, which one is what I will spend the later part of the talk talking about. So now what is an input to this problem? And what does it mean to count solutions to it? So now it's going to be a similar picture up there, except we're going to have constraints on what the circuit looks like. And this is going to be completely contrived. This problem is completely contrived. So now, so this is a Z. So what's going on here? So our gates are in some group that acts on A squared, on string on A squared. So I'm going to define this group in a second. It's the Rubik subgroup of the K symmetric group of this. So I'll define that in a second. And what do we want? Well, we have these constraints around. So I'm not going to have zeros anymore. No ancillary. Instead, I have constraints. So what I want is to count. So I want to count solutions to that circuit, to this circuit, and what that means, what a solution is, it's an input string down here. Okay, it's an input string that satisfies these constraints. So it has to initialize and it has to finalize. So what does that mean? That means X is in so we want input down here that actually is an arbitrary input. It has to lie inside this subset of input. And when we hit the input with the circuit, we want the result to lie in this subset. So we're counting solutions to this problem. So now Z, so what's going on with Z? So later on, Z is this special thing. And you should think of it as a special thing that you don't want, but you have to live with. It's a zombie. So this Z always initializes, and it always finalizes. So if I have a string, an input string, and I know it, and it has some Z's in it, then those Z's are always going to contribute, they're never going to be a problem for deciding if this thing extends to a solution. So this is very much like, so Z later on, so A is going to be some subset of homomorphisms from these small surfaces to G. Later on, Z.
Is there something in your alphabet which is like an actual human? Like
everything else.
so, but I mean, what's that? Like, I could just take everything to be Z. And then,
So A is a big finite set, so there are going to be assumptions about how big A is.
But if I start with if X is all Z's, then I doesn't.
Yeah, so I should say that. So sorry, yeah, so I didn't define this group yet. So this is a certain subgroup of the group of K symmetries of A. So what is it? It's just a commutator subgroup. So this is totally contrived, but it's because later on that's what we're going to get. Yeah. So in particular, what does this mean? If I have a Z and I feed it into a gate, if I have a zombie and I feed it into a gate, well, because we're inside this subgroup of symmetries of A squared that respect the K action, because Z is fixed, the gate will preserve Z. So these gates all preserve the number of Z's that are input into them. So that is helpful because later on, if I have a map from I1 of the subsurface to G that's trivial, But that's going to cause problems, because I'm only interested in surjections if we're looking at Q. And, well, we're looking at H, but we're trying to cook up our manifold so that H is either trivial, every element of H, of M, is either a trivial homomorphism or it surjects. So if you have a trivial homomorphism here on this small subsurface, then it's going to always factor through down here. But somehow, because it's a trivial homomorphism, if you're acting on it with the mapping class group, well, you can't do anything. It's fixed. It's always fixed. There's nothing interesting to do to it. So it's just a technique for dealing with these trivial homomorphisms. So a comment about this. So this is the commutator subgroup of the symmetric group. So I should point out, it's very big. It's almost everything. So it's almost everything, because the quotient of the symmetric group, this one A squared, by this commutator subgroup, doesn't depend on the size of A, as long as A is big enough. The quotient is just going to be the abelianization of K cross C2. So no matter how big you make A, as long as it satisfies these conditions, this Rubik subgroup is really big. And because it's so big, that gives you hope that you can start programming the action. You have lots of gates to work with. So this is a lot. So, are there any questions about ZSAT?
So there's always the stupid solution, and then you want to know how many more.
Yes. There's always the all Z solution,
Yeah.
because the gates just will spit out all Z's at the end. And we're just interested. We're allowing that as a solution, but we're more interested in other solutions. So what we've done in some sense, and what the remaining work is that we've stripped away all of the topology and just built some combinatorial, totally contrived model for reversible computing in an equivariant setting, where that will give us everything we want later. So this problem, if you have certain assumptions on how big the alphabet and the constraint sets are, this problem is going to be Sharpie complete by an almost parsimonious reduction. So like this set here is more like H. It's not like Q, right? Because we're allowing, say, the trivial input, which is like the trivial homomorphism later. So with this in hand, our goal now is to just cook up these things, A, K, I, and F, so that we can do a gadget construction and just replace each of these things here with a mapping class, triangulate the mapping cylinder, and then add handle bottoms, and do it in such a way that the number of solutions here is exactly the number of maps that we're in. So we're doing a reduction from this thing. So what is the A? What's the alphabet? We're going to just, it's all contrived. So we get to pick an alphabet. So to define it, I need to introduce an invariant, an important invariant of homomorphisms from surfaces to G. So this came up, and we learned about this from Nathan's paper with Thurston on random three-manifolds. So learned why it's important. So, we want oriented manifolds, so we get to orient our Hilbert surface. And this is orientation preserving mapping classes, as always. So we get an invariant of homomorphisms by just pushing forward the fundamental class into the homology of G. So this is some element of H2 of G. So you can think of this topologically. You can build a classifying space for G, and this homomorphism, a homomorphism in here, gives you a map from the surface to G, and you can just look at the induced map on the second homology. So we call this invariant the Schur invariant because it takes values in the Schur multiplier of G. So it has a really nice property pointed out by Livingston. So if I have two homomorphisms, and I know they're both surjective, so F1 and F2, from some surface, sigma g, then the values of the Schur invariants will be the same if and only if these homomorphisms are stably equivalent. And roughly what that means is you can connect some F1 and F2 with some homomorphism from some other surface that's trivial. And then the resulting maps from this bigger surface are equivalent under this mapping class compaction. They're in the same order. So that's the kind of topology that's lurking behind this thing, and why it's useful. So once we have that, we can define our alphabet. So what we're going to look at are surjections from sigma g, so sigma g is one of these small surfaces, to g. And we only want ones that have a trivial Schur invariant. So if you think about it, this is a free ought g set. If I have a surjection from pi1 from anything to g, if I have an automorphism of g that fixes that surjection, that automorphism has to be trivial. So our zombie symbol now, as I indicated, is going to be the trivial homomorphism. So this is highly not surjective. It does have a trivial Schur invariant, and it's fixed by every element of the automorphism group of G. So you can see this contrived thing, ZSAT over there, we're working towards it. There's a reason it's contrived the way it is. So our alphabet now is, well, we just combine these two things. We have these Schur trivial surjections, and we toss in the zombie to G. And we're going to pick our genus later. It's going to be large enough, and how large, I have no idea. But there's interesting things to think about. So that's the alphabet we're going to work with here. I want to say something briefly about the case of knots. Because in the case of knots, like how do you get this kind of Schur type invariant for knots? And the way there is to think of a map from pi1 of a punctured surface as a branched cover. The punctures are the branch points. So and it turns out there's a classifying space for these things. So now, yeah. So we have some constraints. You don't allow arbitrary branch types. You want branch. So these are branch G covers with branch types in the conjugacy class C. So remember C at the very beginning of the statement in the second theorem was just some fixed element of G that we're kind of fixing a color for one of the arcs of our knot. C is its conjugacy class. So this classifying space here is it's the usual BG, and then you glue on a bunch of disks. So if you have a smooth manifold and you have a map into this thing, well, you get an induced C branch G cover on that over that manifold. So I won't say too much about this, but that's what it is. And so this LC, I should say about LCVG. So this is the component of the loop space of VG that is represented, that kind of represents the conjugacy class C. So it's all maps from S1 into VG, so that the loop you get is somehow represents an element of that conjugacy class. And then you glue on a disk to the usual VG by evaluating the boundary of the disk at that loop. So, and then you get a Schur invariant. So if you have a surface and a map from pi1, you puncture it, and you know something, you have a map from pi1 of this puncture thing to G, and you know something about the punctures, where they go, then you wind up getting a homological invariant, just like before. Except now it's in a different H2. It's H2 of this weird space, which looks pretty daunting because you're gluing on like a loop space, but it's actually, the H2 is pretty tame. It is infinite, but it's pretty tame. I can calculate it for you if you want. You could maybe do it yourself. You just use the Mayer-Viator sequence for this point. So we use this thing to define the alphabet in the case of knots. We're writing this. So I've told you what our alphabet is. Let's remind ourselves, it's right there. We have the trivial homomorphism, we have surjections with trivial Scherner. So now, there are two things we need to do to get to be able to take that ZSAT model and turn it into a manifold. So we need to study binary gates. So if we take two of these surfaces that are sitting next to each other, we want to know, well, if I start Dane twisting, or doing some products of Dane twists on curves that are supported on the union of these two subsurfaces, or this saddle with this saddle, then we want to know, well, what can we get? What kind of gates can we get? Can we get this full Rubik subgroup here? So, spoiler, yes. I mean, that's why we picked this. That's why it's contrived the way it is. It's just that the reduction from here to here has nothing to do with topology. So that'll be a theorem that we're going to discuss. And moreover, we want it to be the Torelli subgroup because we want homology spheres. So I'll say something about that. Now, in some sense, the hard part for us, and the reason everything's contrived the way it is because we want to make sure we don't get spurious homomorphisms. And this was something that came up in Arnaud's talk, which is the easy part of his reduction was showing that if the formula is satisfiable, then there's an embedding of the thing. The hard part was showing that if there's an embedding, then it's satisfiable. And that's kind of the hard part for us, which is showing that building our manifold to ensure that every homomorphism from its pi 1 to G comes from something it's supposed to, comes from something, from a solution to the circuit over there. So that means not only do we need to pick, well, we know what A is, not only do we need to know something about how the mapping class group acts on A squared, we need to know something about what's going on away from A, or A squared. So, so the technique is to treat these things, so there are bad digits, right? So if you have a homomorphism from the surface to G, and it's not in the alphabet you care about, that's somehow something you don't want to contribute. You don't want it to contribute to the final answer here. So what we do is just make sure that if I have a bad homomorphism here, every gate that will ever act on it preserves it on the nose. So we kind of treat them as zombies. So if a bad homomorphism goes into a gate, it just comes right out the other side of the gate, unscathed. And that technique makes sure if it's a bad homomorphism and it's not trivial, well, it can't factor through both of these handle bodies at the same time. So if I look at its value on the subsurface, well, when it goes through every gate, what it looks like on this subsurface, it looks exactly the same. Because it's a non-trivial map, it can't factor through both. So I can say more about that. But, so how do we achieve these two things? Well, we start with the theorem of Nathan and Thurston that looks at these kinds of questions, but they work non-equivariantly. So what they do is they quotient by this ought G action. So what's that theorem? So G here is nonabelian and simple, as we assume for our main theorems. And the genus has to be large enough. And what they show is that the image of the mapping class group acting on, well, basically our alphabet, but you quotient by the ought G action, so you can just look at equivalence classes of these homomorphisms. Well, you get the entire alternating group. So you get as much as you could possibly hope to get, right? So the mapping class group couldn't possibly surject onto the full symmetric group because the mapping class group is perfect. And the symmetric group has a Z2 quotient. But you could hope for it to get on to surject on the alternating group, and they show it does. So that's great. But as I indicated before, we need to understand a little bit more. So we want to understand the action on RG0 and not the quotient by ought G. And we simultaneously need some control over the spurious homomorphisms. So we're going to refine that theorem. So as I've said already, so if I have a mapping class group acting on a set of homomorphisms, well, there's another action of the automorphism group, and they both commute. Well, they commute with each other. And that's equivalent to saying that the image of the mapping class group inside the symmetric group on that set is actually constrained to lie inside the set of bijections that commute the LG action. Right? That's what this is. That's the definition. So, and similarly with our A, you land inside. You look at the action, the image inside the symmetric group on A, you land inside there. So that's one constraint on what can happen when we try to lift equivariantly. So, and now we're also concerned about things that are inside A, maps that are inside A. And one thing to observe is that if we have a surjection and it doesn't have a trivial Schur invariant, then in fact it will never contribute to the final count. So if I have a map from this surface, this small surface here, and it surjects on the G, well, I don't even need to know that. And I know that it's Schur invariant, so it's homological invariant inside H to a G is non-trivial, then that map can't possibly factor through that handle body rate. If it did, then it would have, right, that's exactly what it means. Well, it would be null boarding, which is the same as null homologies. So what that means is we only really need to consider all the maps. We don't need to consider all of our at G, we just need to consider those maps that are also, that have trivial Schur. And non-surjections. So these two observations, what they let us do, we can whittle down the problem. We want to study the action on, so again, RG0, so these are the surjections with trivial Schur invariant. And then we look at everything that isn't a surjection. And we're also going to toss in H1, because we want to know something about, can we say something about getting Torelli mapping classes? So here is our theorem. So the mapping class group acts on this big thing, and each of these three sets is preserved by the action. It's invariant with the action. So that means that the image of the mapping class group is going to land inside this product of groups. And so we discussed why. So if you look at how it acts on the first term there, we discussed this. Just because we also know this. And then, well, when the mapping class group acts on H1, you know it preserves the intersection form, so it lands not inside all of GL of H1, it lands inside the symbolic. And in fact, it's surjective, and we actually need to know that for groups. So the theorem is that the image of this mapping class group inside this product of things contains the Rubik subgroup we're after. So there's a lot lurking here. So this is a subgroup of this product. So what do I mean by that? Because of course this thing right here is a subgroup of this term in the product. And well, so what I mean for it to be a subgroup of the product is that, well, it's trivial over there. So, and that's exactly what we wanted for our spurious homomorphisms. This is saying that you can act how you want. You can act as the Rubik group on A, while simultaneously ensuring that you do nothing to the non-surjective maps. You just fix every one of them point-wise on the nodes. And then you can do the say the same thing about the homology. You fix the homology point. So you're acting trivially on homology, which means you're Torelli. You're acting trivial on non-surjections, which means this zombie trick will work to make sure that the spurious things don't count. So that's the theorem. There's a lot of group theory. I don't have to study the proof of Nathan's theorem. And you have to know something about the symplectic group. You need to know it has the congruent subgroup property, which means that every finite quotient of it factors through a congruent subgroup. Basically, so what that means is that the finite quotients of this thing are never alternating groups. So somehow this thing's quotients are, so these two things don't have the same quotients. Which allows you to use group theory to decouple these actions. So this theorem is morally a theorem for not binary gates, right? We want sigma 2G. We want to act on A squared to get binary gates, because that's what ZSAT does over there. But we have so the theorem is more about a single gate. So if I look at this individual surface and look at the maps on it to G, what can we say about the mapping class group just acting there? So we want to say something about two surfaces banded together like this. And, well, we can do that. So we just apply the theorem we have, and kind of, there's some annoying thing where you have to keep track of base points, and you can make sense of A squared. And we apply the theorem, and we get that we can find Torelli mapping classes. So for every element of this Rubik group here, we can find Torelli mapping classes that act as that element on A squared and fix everything else. So that's the important mark here. So now we're ready for our reduction. So we're going to take K to be on G. So our group with respect to which everything is equivariant. A is the alphabet we discussed. Z is the zombie digit. This is the trivial homomorphism. And then I and F are initialization constraints. So I is going to be the bottom initialization constraint. That comes from the fact that you have to factor through the handle body on the bottom. And F is the one on the top. So you could write down what that means explicitly, but you're basically saying the value of the homomorphism on these bigger curves is trivial. So those are all the choices we're going to make for our Z set. Well, then you have to check that the sets have decent cardinalities so that you get the sharp hardness you're after using the lemma from before. And that's what to show. And now, given Z, given an instance of this version of Z set with these choices, we just get a mapping class. So we picked our gadgets back here, and now every time you see a gate, you know it's some element of this group, and now you just replace it with a mapping class that acts on you. And then you wire it up exactly like that's wired up there, except now you're acting on that surface of it. And, well, so that's just an element mapping class group. We really want to triangulate three manifolds, so well, we have to glue the two handle bodies and triangulate. It's not hard. Yeah. That solves those, yes. Not so bad. So this whole construction is linear time, because you're just doing a gadget construction. You're just sticking some triangulated thing in each of these, and each one of those costs some constant amount. So this thing is a homology sphere because all of our gadgets were Torelli. And we get what we need. It's actually a reduction exactly because of this zombie condition. So very technical condition, but if you stare hard, I've showed you everything you need to actually verify that this is true. Not to prove the theorems, but to verify this formula using those theorems and the choice of the gadgets. So that's the reduction. That does it. Any questions about the reduction? Yeah.
How big is G?
Little g?
Yeah.
I have no idea.
Well,
I have to pick some little g.
But don't you need to have a linear bound on its size if you want to construct everything in linear time?
Well, I just pick there's some little g big enough, 1,000, I don't know.
Okay.
And then the theorems go through.
So you fix that.
I should have said that. That should have been bullet point 0. Yeah. So I fix little g so that the theorem back here holds.
Or as a constant.
Yes, it's a constant. Yeah. And then I pick these k's and i's, and
So it's important. So the gates are all pretty small, right? The gates are all binary.
they're binary. Yeah. We get away with that because A is big.
Right.
So I lied a little bit up here. This problem is not Sharpie complete because we're only using binary Boolean gates. You need ternary Boolean gates. So you need the topology. There might be some way to get around it, but the naive way you want ternary gates.
You don't have. But I have some stupid question for Charlie.
Any other questions?
We might need to do a little bit of work to get the correct variables next to each other.
Oh, this is a planar circle.
Planar circle. Oh yeah.
I should have said it. It's planar. I drew them all planar, but it's planar.
Yeah.
So. Okay, so that's a reduction. Several questions we can ask about it. Can we make the manifolds not just Torelli, but hyperbolic? I don't know how to do it. It sounds, I expect it should be true, but I don't really have a good sense of how you would start it, because this is a gadget construction. Right? We're picking gadgets, we're picking mapping classes that only act on like 2 small pieces. But you want a pseudo-no-self. And the property of being pseudo-no-self is something in the whole surface. Do you think we need to do something?
Well, you're seeking something stable at the beginning.
Yeah, but it might be too big. I don't know. Yeah. So we have this corollary about finding covers, 5-sheeted covers. That's difficult. What can you say about 3-sheeted covers or 4-sheeted covers? I don't know. Kind of generalizing, is there a dichotomy theorem? Arnaud alluded to this, that this is a trait satisfaction problem, and those things are all either NP complete or they're NP. So is there a clean dichotomy in terms of the group G that it tells you the complexity? So are solvable groups easy and unsolvable groups hard? And how large is large enough? How big do we have to make G? So there's kind of some group theory lurking there. Things about one question that pops up is if you have a finite group, you can ask, well, what's a minimal, and you have an element of its H2, its Schur multiplier. You can ask, what's a minimal genus? What's the smallest genus representative of that homology class? So something you might be able to do in principle for some of the simple groups, just doing a calculation using hat or something. So related to all this and things that have kind of come up the last couple of days, just a question is there an effective residual finiteness for 3-manifold groups? And something that has bugged me, which is that counting these invariants looks a lot like these circuits. So can you use that to say something about genus? Right? Can you somehow say that there are manifolds where this invariant certifies the genus, or lower bounds the genus, and can you use that to relate the 3-manifold genus question to some question for some kind of combinatorial question for reversible circuits? You're trying to basically play the game, how do I minimize the number of ancilli? And you might, I'm not quite sure, but that problem feels like it's hard for the second level of the polynomial hierarchy. So maybe the problem of genus of 3-manifolds. Okay, so that's it.
Are there any questions for the speaker?
Yes, so with the 3-manifold genus, that's the Hagar genus?
Yes.
Okay.
Yeah, maybe I should have said Hagar genus.
If not, then let's thank you for coming.